Okay, Laura, over to you.
Okay, perfect. So I'm going to just cover a little bit about Greenfix just to start, just before Bryan goes into the full presentation. So as mentioned, Greenfix has been trading since 1982. And within that time, we've become the leading designers and suppliers of soil stabilisation and erosion control within the UK. In association with our partners, which include Presto Geosystems, Greenfix has developed a comprehensive range of products and systems to combat the complex and diverse problems associated with erosion control and soil stabilisation. Greenfix's extensive product range extends to offer solutions to a variety of applications, including house building, river restoration, coastal erosion, and of course, rail embankment and track stabilisation. Greenfix became corporate members of the PWI in 2021, and since joining, we have seen great value in the organisation and are continually impressed with the level of training, knowledge, and support they offer their members. We go to slide 2, please, Bryan. Thank you. Along with GeoWeb Geocells, which Bryan will discuss in more detail, Greenfix offer a wide selection of products suitable for rail applications. These products include our cover mat, which is a pre-seeded erosion control blanket. These blankets are made from natural fibres and come pre-seeded for quick and easy installation on site, which eliminates the need for hydroseeding or hand casting seed. We also have Aeromat, which is our unseeded erosion control blankets. These are available in 3 different fibre combinations for medium and long-term lifespan, which include 100% straw, 50% straw and 50% coir and 100% coir. We also have our F3 flame retardant erosion control blankets. These are designed for use in areas where fire hazards need to be considered, such as railway embankments. The F3 products combine all the benefits of our pre-seeded and steel reinforced erosion control blankets with the addition of fire protection. And then we also have our GeoCoir and GeoJute erosion control messes. These provide surface stability to steep and aggressive applications such as watercourses and areas of high wind exposure. Both the GeoCoir and GeoJute slow water runoff, and the mesh also allows for planting in areas where shrubs and plants may be required. Then moving on from our erosion control blankets, we also have Park Pave, which is a porous paving system. And this offers a durable paving solution for heavily trafficked areas such as site compounds, emergency access roads and car parks. And then finally, we have Envirolock, which is a vegetated, mechanically stabilised earth wall system for retaining walls, slope stabilisation and shoreline protection. And at Greenfix, we are committed to delivering the highest quality service to all of our customers, offering help from the early design stages to guidance at installation. So please do get in touch with us if we can ever assist you with any of your current or future products, and we would definitely be able to help. I'm now going to pass you on to Bryan.
Thank you, Laura. Good afternoon, everybody. Thank you for joining us today. I guess I'll get right into it. So a geocell system consists of 2 main attributes. The first is the cell size. The cells typically come in 3 diameters, 21, 26, and 45 centimeters. The cell wall heights include 75, 100, 150, 200, and 300 millimeters. The panels also come in different section lengths to best suit your site conditions, and typical lengths range from approximately 5 to 10 meters. The actual cell size and height depend on the site-specific project details and site conditions. You need to make sure you receive a design from the geocell supplier based on your site-specific material properties. We recommend not using any standard charts or tables, since no 2 sites are alike. The ultrasonic welded seam, where all the connecting points are located, is very important to the function of a geocell. The stronger the seam strength, the better performance of the geocell. A strong seam allows for better lifetime performance. Geocells are typically produced from high-quality virgin HDP or high-density polyethylene resin for consistently strong welds at the seams. while also maintaining semi-rigid ductile properties, high stress crack resistance, and overall toughness. To avoid weld failures and the damaging effects of to avoid weld failures and the damaging effects of differential sediment, uniformity and performance across all elements of the geocell system is much more important than stiffness alone. Here you can see a typical geocell panel. It comes tri-folded on a pallet. Each section has a nominal width of 2.6 meters with variable panel lengths, as I stated previously. The panels are flexible, opening like an accordion, so they can follow the natural contours of the site. In order for a geocell to perform uniformly, it is critical at both the factory welded junctions, that's the internal junctions, and at field junctions that connect individual panels perform at a level that is commensurate with that of the cell walls. Therefore, an incremental improvement in one characteristic, for example, cell stiffening, is only valuable if a complementary improvement has been made in the other components of the system. Recently, we've noticed a concerning trend where some providers present performance data that appears to equal industry accepted standards on the surface, but then they add disclaimer language in the fine print at the bottom of the specification page, saying that their specifications are subject to change without notice, or the information shown is for general purposes and not intended for design. So just a heads up to watch out for this type of trap, especially if you get hit with a request from a contractor on one of your projects to evaluate a substitute product. Specification sheet should contain no disclaimers, and the manufacturers should stand behind their numbers so you can deliver certainty in the solution as you build with materials you can trust. Geocell 3D works this way. When a vertical load is applied, the active earth pressure in the loaded cell pushes back against the passive earth pressure in the adjacent cell to form a stable system. So each cell helps support the ones around it. The geocell walls also transfer hoop stress, which is important in keeping the system intact, and creates what is known as the mattress effect. So the strength of the seams around each cell, material stiffness of individual strips, and the connection method between panels are all important factors in determining how the geocell system can improve site condition. So strong seams, semi-ductile resin properties, and integrated connections are critical to uniform performance of the installed system over the life of the project. In a low support scenario, vertical deformation can only occur with compaction or through lateral movement. So by spreading out the load in the classic approach, one can reduce compaction of near surface soils, but only with a cellular confinement can you ensure no lateral shifting or rutting. Here you can see the stresses on the subgrade with the unsupported subgrade on the left and the geocell reinforcement on the right. Notice how there's a complete elimination of the highest stresses at the surface with geocell reinforcement. Stresses are reduced and distributed over a wider area, which we call the mattress effect. The mattress effect reduces stretch reaching subgrade and leads to a significant decrease in deflection and rutting. The second main attribute of the geocell system is the infill. An important benefit of any geocell system is that even a low quality aggregate, sand or salvage material can be used to infill the cells. So using salvage materials, low quality aggregate or sand can save a significant amount in material and hauling costs. And we can also eliminate fines when desired, since the cells provide the confinement and aid compaction of cohesion lift soils. Without fines, you can significantly improve drainage, let the water flow freely through the system, preventing poor pressure buildup and global failure. The ability to use sand and low quality aggregates really sets geocells apart from other geosynthetic products. Those products typically require high quality materials with high friction angles to achieve optimal performance. With geocells, low friction angle materials are just fine. The panels achieve their full potential, even with the poor materials, which can, like I said, can lead to a huge cost savings. Here you can see the impressive load benefits. This is a fully loaded dump truck on a partially filled geocell panel over a very soft subgrade. You can see how the cells push back against each other to support the load, and that only the adjacent cells need to be filled for support. A great benefit for using geocells is that you don't need to have every cell completely filled before the road is usable. You can reduce construction time and materials with this approach. Locked up a little bit here. There we go. I'd like to talk a little bit on some past research and testing with geocells under trap. The first real research completed in the 1990s at TTCI which provides research and testing for all aspects of railroad and associated equipment here in the U.S. The facility has approximately 50 miles of track. The research we are going to look at today was conducted on the fast high tonnage loop. Geocells was installed in section 29, which is about a 700-foot section, the high tonnage loop. The loop is continuously loaded, except when new materials and ideas are tested. This was a 2.5-year study, and it was also compared to a control section. Mississippi mud was imported to the site. The soil was a high plastic clay, having a CBR less than 3% with a 30% moisture content. Without the geocell, the concentrated loads and high pressure in the ballast, squeezed the clay outward and upward, resulting in unacceptable track profile and a contaminated ballast. However, with the geo system, the load was distributed over a larger area, which significantly reduced ballast pressure, which led to stiffening of the sub-ballast layer and a load to the subgrade. Acceptable track geometry was maintained throughout the 2.5-year study, and over 206 million gross tons of loading were applied. Here you can see the impressive results. Without geocells, tamping was required on average every about 15 million gross tons to stay within the track profile of 0.5 centimeters. With geo and over 260 gross tons of loading, the vertical track alignment never exceeded 0.7 or 30% of the allowable, and the cross track alignment never exceeded 0.5 centimeters during the 2.5-year test period. At one point in the test, they actually brought in 100,000 gallons of water and dumped it over the area to induce failure, but no appreciable effect was measured, and the test section is actually still in place today. So based on the success of the previous testing, we wanted to use recent technology to confirm the stabilization benefits of Geocell. The testing program was Geocell reinforced ballast over a week subgrade was performed at the University of Kansas. In addition to the University of Kansas research, Oregon State performed state-of-the-art 3-dimensional finite element modeling to analyze the reinforcing benefit of geocells in railway application. Each test was instrumented with earth pressure cells and smart rocks, as you can see shown on the lower left side of the slide. So each smart rock included a motion and vibration sensor that could record rotation, translation, and orientation. Earth pressure cells were used to measure the vertical stresses and displacements at the interface between the ballast and the subgrade. Once I said, the research was conducted at the University of Kansas under the direction of Professor Yi Han, who has been conducting research on geocells for over 20 years. Ben Lashinsky from Oregon State, who did his PhD thesis on geocells, conducted a finite element analysis, and Professor Hai Hug from Penn State provided the smart rock technology. The testing consisted of equivalent 37,000 pound wheel loads, speeds of 75 miles per hour, and 136 pound rail. They varied the subgrade from a 0.5 CBR up to a 5 CBR. We did a total of 8 different tests. This is a 3 control set tests and 5 geo-supported tests with a minimum of 1,000 passes. To evaluate the ballast movement under cyclical loads, like I said, the smart rocks were added to the ballast, not only inside of the geocells, which you can see here, but we also placed smart rocks halfway between the bottom of the tie and the top of the geocell panel. This one, the ballast was 300 millimeters, so these smart rocks were 150 millimeters below the bottom of the tie and 150 millimeters above the top of the geocell panel. Here you can see a little bit on how the smart rocks measure movement of the ballast rock, both rotationally and also in all different directions. So this slide shows angular velocity, which is how fast the particles rotate. So this is the results of the testing. The 2 graphs on the left show where the smart rocks were placed in the middle of the ballast, between the bottom of the tie and the geo panel. The 2 graphs on the right are smart rocks placed inside the geo panels. You can see the difference between the control section and the geocell stabilized section. It's very interesting that the stabilization section not only controls the ballast movement in the cells, but also you see the graphs on the left which show how stabilization controls movement on the unconfined ballast layer between the tie and the GUM. So this section right here is below 150 millimeters below the tie. So you can see the control section without geocells and the section with geocells. You can see how much it stopped the rotation of the ballast, once again, between the tie and the cell, and then inside the geocell. So this slide shows angular acceleration, which is basically how fast the particle moves when subjected to cyclical loads. So just like in the previous slide, you can see how the geocell stabilization controls movement in the cell and also below the tie. So here, this section here is the control. So you can see how the ballast is moving below the tie and between the top of the geocell and then inside of the geocell. So the test results clearly show that GM stabilization significantly reduces particle acceleration and velocity, not only in the cells, but below the tie. The results show that stabilization can effectively minimize the movement of the ballast particles by providing lateral confinement so that the breakage, vertical pressure, attrition, and lateral spreading is minimized and performance can be significantly improved. So by controlling ballast movement and rotation, this will lead to decreased tamping and reduced maintenance, will directly lead to cost savings. Even though this research was done based on a railway loading, it applies pretty much to any cyclical load. We also validated the data using a state-of-the-art FEM analysis to confirm the reinforcing benefits of geocell stabilization. Finite element analysis is used basically to solve very detailed problems by looking at both an unstabilized cross section shown in the left and the stabilized section in the right of the slide and how they change under cyclical loads. So the analysis used partial differential equations to determine the results. The lower picture on the bottom right examines the output showing the vertical stresses at a subgrade of 0.5 CBI. So the use of the geo confinement was very effective in redistributing the vertical stresses on a subgrade, resulting in a larger area of subgrade mobilization and shear strength and reduction of deformations. So geocell reinforcement decreased the pressure at the ballast subgrade interface by over 50% for weak subgrades. Geocell reinforcement also increased the load-bearing area of the subgrade and resulted in decreased interface pressures. The decreased pressure in the subgrade will result in lower subgrade settlements. So I'm going to take some time to discuss some rail applications. Geocells can be used under track in all areas from basically mainline track, areas subjected to heavy stresses, including bridge approaches, crossings, turnouts, frogs. Geocells have installed under track for almost 40 years now with great success. And the industry has lots of case studies that they can share on many different types of installations. This is a project assisting a mile to new track for Network Rail on their northern hub on the Bolton X10 line around mile 17. Parts of the track that were enhanced on their hub project are located on very soft grounds with very low shear strengths. So as a result, the standard required depth of track that could be as high as 1 meter, which can basically lead to some very expensive track to construct. The Network Rail track bed investigation team was tasked with finding alternative design solutions to reduce the required depth of construction on these patches. So using Network's Rail in-house numerical modeling capabilities and Presto design method, the use of geocells was proposed as a viable alternative track bed design solution. Numerical modeling was used to quantify the allowable reduction of track bed depth if geocells were to be installed so the track bed behaves in a similar manner as if the standard design solution was to be implemented. The model was further used to iterate different geocell layer thicknesses and compared to performance indicators with the baseline values from the standard track bed design. The iteration showed that using a track bed design that consists of 250 millimeters of ballast, 150 millimeter deep geocells filled with a granular infill, and a 50 millimeter sand layer would provide similar performance to the standard design solution. It would save 80 millimeters of construction depth. It's also important to point out that the reduction in required track bed construction, which was 40%, due to the use of the geocells on the Northern Hub project, also reduced the cost of the track enhancement by approximately 22%. Here are a couple images on the installation. You see a non-woven geotextile separation layer was placed over the 50 millimeter sand layer. 150 millimeter deep geocell panels were placed and filled with a granular material. The contractor can basically spread out the infill into the geocell and compact it prior to placing the ballast layer. After the successful installation of the geocells on the Bolt Nuxle line and opening the track to traffic in early 2017, the track geometry was monitored on a monthly basis. The slide shows the track quality standard deviation for 1/8 of a mile for the worst top 35 meters and the mean top 70 meters. So from the figure, it can be noted that track quality has significantly improved to an excellent condition for both the top 35 meters and the mean 70 meters. So to understand the effect of the geocells, the track quality and rate of deterioration after the geocell installation can be compared with track quality deterioration after the most recent renewal before the installation, which took place in 2002. And here you can see the last recorded installation in 2002, increase in track bed deterioration, so maintenance work, and then installation of geocells in 2018. You can see the comparison between the track quality after the last major renewal in 2002 and after the installation of geocells in 2017. So can you observe from the table here that after installation of the geocells in 2017, the track quality and deterioration improved significantly. So the deterioration after renewal in 2002 ranged from 0.7 to 0.9 millimeter per year. The geocell installation in 2017 has seen the deterioration values from 0.1 to 0.5 millimeters per year, which is a drastic improvement in the quality of that area track. So based on successful geocell installations, NetworkRail decided to develop a guide with the goal to provide a summary of the benefits from research and testing, design recommendations, and best practices for installation of geocells. In August 2020, NetworkRail issued the use of geocells in UK Railway Trackbed Technical Guide. The guide was supported with review of the railroad and lab testing at the University of Kansas, existing geocell design methods, case studies and successful installations, and installation methods. So prior to final approval, the guide was peer reviewed by 6 recognized professionals with rail experience. This guide was also used as a reference for the NetworkRail Trackbed Standard, NRL2 TRK, issue number 2, which was issued on September of 2020, which contains detailed design information in the guidelines for geocell. So the standard basically provides the guidelines for engineers to include geocells in their designs. So this is another project. This is Warrington, northern UK, approximately 3 miles north of Peterborough Railway Station. Major works have taken place at the Warrington Junction, implemented by NetworkRail. The aim of this project is to increase the capacity for passenger trains on the East Coast Main Line as part of the $1 billion upgrade. This scheme, which is referenced to as either Warrington Dive Under or Warrington Grade Separation, involved the building of new 2-track railway line which tunnels under existing line. The line opened in 2021 and removed constraints to the train timetables caused by the slower freight trains on the Great Northern Route, which currently have to cross over to high-speed East Coast Main Line. This project included the construction of 1.9 miles of new line with geocell utilized to improve track bed stiffness in areas with poor soils, to aid in drainage, and to reduce the depth of excavation required compared to the traditional track installation. The new track was installed in accordance with the new NetworkRail specification NRL2 TRK, which I said before, which aims to improve track stiffness and reduce maintenance. This area had a lot of very poor soils, and here they went with an enhanced woven geotextile with a strength of about 40 kilonewtons per meter and 200 millimeter geocell panels filled with the local sand. Geocells can be utilized to improve unattractive areas with poor soils, aid your drainage, and reduce the depth of excavation required. So one of the advantages is using geowells, like I said before, is you can use any type of grinding material, even coarse sand. You can see on this installation, they are using a very coarse sand to infill the geocell panels. Geocells are very flexible. You can use, like I said before, you can use any kind of low quality infill or even recycle ballast, with the only requirement being to keep the fine content less than about 10%. Here you can see where the contractor wanted a pretty precise installation. So they actually use stretcher frames, stretcher bars to keep the geocell panels open prior to filling. So basically they just spread the infill out You can see there's a GPS unit on that bulldozer, and then compact to the top of the Geocell panel. Since Geocell are flexible, I wanted to show this mainline track. This is a project for a heavy coal line. Subgrades ranging 1 to about 3%, most were around 2%. Project consisted of about 10 miles of track that had a decent subgrade wasn't that bad, but the ballast had become really fouled and required ongoing maintenance. So their interesting point of many of our projects, or any Geocell project for that matter, is that we can reuse that salvage ballast. So you can see here the salvage ballast was stockpiled next to the rail. So you can see that here they just, nice cursor. Here you can see they just took the existing ballast, pushed it to the side, and used it to infill the Geocell panels. So you can imagine how much cost savings can be achieved on a project using salvage ballast. As stated here, this was a 10 miles of track at 150 millimeter Geocell. So they saved in bringing over 12,500 cubic meters of infill. So you can imagine how much cost savings the use of the Geocells provided the owner, including not only the infill, but also the hauling costs and the associated reduction in carbon emissions due to using the salvage ballast. You can see just the salvage ballast compacted in place. And this was actually a 200 millimeter ballast layer going in. You can see in the sleepers and rails. So once again, just to point out, you can use any type of low quality aggregate or sand or recycled materials for a Geocell installation. A lot of high stress areas. High stress areas subject to maintenance or one of our bridge abutments. You hear a lot of the railroaders talk about the bump at the end of the bridge due to long-term consolidation and actually settlement at the bridge abutment. As we know, bridge abutments are very high stress areas when you transition from a solid structure to a prepared subgrade. And once again, that bump at the end of the bridge is a big problem. This is a picture actually of a project we did here in the States. This is one of the Class 1 railroads. They use Geocells at basically almost all of their new bridge abutments or their maintenance areas to control that differential sediment and the bump at the end of the bridge. This is a project we recently did, like I said, down in Texas this fall. There are different types of installation methods that we can use at bridge abutments. On this project, we used one layer of Geocells in enhanced woven geotextile. Once again, about a 40 kilonewton per meter geotextile. Typically, we use 2 panels in width, so about 5.2 meters, and approximately 13 meters in length. So the panels provide an acceptable level of stress distribution off of the bridge. And depending on the amount of sediment that is expected, sometimes we provide 2 panels stacked on top of each other at the bridge abutment and then transition to a single layer. So this decision is pretty much based on the speed and the elevation of the bridge abutment. So this is a low bridge abutment, so there's only 1 panel, about 13 meters in length. If it's a very deep bridge abutment, we'll have 2 panels coming out, 1 panel in length, and then we'll transition to 1 panel just to dissipate that stress. So also, Geocells can deal in a lot of high stress areas, such as crossing, diamonds, intersections. Here's a couple of projects I want to talk about. So we deal with a lot of high stress areas on a daily basis, like I said, including the crossing, diamonds. Here's a couple interesting projects. This is a grade crossing once again down in the lower part of the United States. So existing crossing consisted of standard reinforced concrete panels and wood ties. So the crossing is located adjacent to a concrete plant. And the heavy trucks were damaging the crossing. The system prematurely failed due to the excessive braking and acceleration forces being transferred through the crossing to the subgrade below. The concrete panels did not hold their position, despite actually being lagged to the ties and tack welded to each other. So several panels actually failed completely and had to be placed and patched with asphalt. So we worked at Class 1. Once again, we provided a high strength woven geotextile, 40 kilonewtons per meter, and 150 millimeter Geocell panel to dissipate forces from the traffic in rail, while basically providing a floating platform to absorb the lateral braking and acceleration forces. So here the Geocells were placed under the crossing and extended about 13 meters on both sides. This project was also interesting because this was the first composite grade crossing. You can see the composite grade crossing here on the left side of the slide. You can see the first trade through the grade crossing prior to finishing infill of the geocell. And since replacement in 2015, there's been zero settlement or deformation of the roadway or the tracks due to loading and braking. So in summary, geocells can be added to rail project to provide a more stable and longer lasting ballast, which will reduce maintenance and repairs. The ability to use low quality aggregate, coarse sand, or even salvage ballast can save a significant amount of money. Also, the ability to reduce the stress on a subgrade will control differential settlement and can potentially reduce sub-ballast thickness, leading to additional cost savings. Geocell research and testing at the University of Kansas show that we can significantly reduce ballast movement and rotation, not only in the geocell panels, but also between the bottom of the tie and the top of the geocell. Controlling movement and rotation of the ballast will reduce attrition, camping, maintenance, and also reduce costs. Need to work with the geocell manufacturer to provide a complete solution, including the type of geotextile that may be required, the geocell depth, and the sub-ballast depth based on your site-specific conditions. So a little bit of time, I'd like to discuss how geocells can be used to protect slopes adjacent to railways, and also briefly discuss some earth retention. Geocells for slope protection is a very flexible solution. It can use different types of infill depending on the project needs. Topsoil can be used if a vegetative surface is desired. A lot of the rail embankments we do utilize aggregate infill to reduce the need for cutting and keep animals off the slope. We can also use concrete in projects where no maintenance is desired or areas that are subjected to heavy rainfall and high shear stresses. On this slope project, you can see aggregate infill was chosen for the nearly 20,000 square meters on two sides of this embankment for erosion control. They wanted basically a low maintenance cover. You can see how material delivered at the top of the slope and the implementation of the geocell panels reduce handling and actually truck traffic in the surrounding areas. For all slope applications, sometimes acreage is typically required. Acreage can be with steel or plastic pins driven into the subgrade. For steeper slopes, tendons are run through the geocell panels and run to the crest of the slope where they're tied to a pipe deadman or earth anchors. Here you can see the panels on this project being filled with crushed aggregate and installation of the steel pins for anchors. Infill is done always from the top of the slope to prevent panel overstretching. Here you can see the steel pins being ready. This guy here is using a pneumatic hammer, vibration hammer, to drive the steel pins into place for anchors. So just a close-up picture showing the geo panels extended under the bridge abutments and getting infilled with the crushed aggregate. And here's a picture of the finished slope a couple of years later. So the aggregate is still in place and has not been washed away by rain and snow melt. This is a project for a new siding that was done. The geocell is used for slope protection, but also for channel protection for routing water away from the track. The installation was about 42,000 square meters of 100 millimeter deep geocell panels filled with crushed aggregate. The area does not get a lot of rain, but when it does, it typically is short and large bursts. So railroads use geocells for erosion on these sidings and to eliminate any maintenance work. Here you can see the panels prior to infill placement. Large riprap was provided on the bottom of the slope in areas next to the culverts for some additional protection. And here you can see a large culvert pipe under the rail with the riprap protection. Like I said, the area receives quite a bit of runoff from the nearby areas, which you can see leads to the size of that culvert pipe. So as with other applications, the geocell manufacturer should provide a full set of calculations based on the material properties, their panel connection device, and load transfer device if they're using tendons. It is not recommended to use standard tables since no site is the same. The calculation needs to include the type of anchorage that is recommended, whether it be pins or tendons, and also include the amount of anchorage required. And if tendons are required, calculation for the crest deadband that's buried at the crest of the slope should include the size of that pipe and also the depth. They should also provide a cross-section drawing showing the type and amount of anchorage for the pin or tendon options. This project here uses polyester tendons and a solid wall PVC, actually a PVC deadband buried at the crest of the slope. So the tendons are just basically tied here. You can see the pipe dead man buried almost a little over a meter in depth. So here the tendons are run down. The geocell panel, just like hanging a set of drapes. You got the dead man on the top, tied tendons run down through the geocell panel. And these shows you a plan view showing the layout and the type of anchorage. So in summary, geocell slope protection has great flexibility of design, a variety of infills to meet your project needs. Steep slope protection is not out of the question when using geocells. They've been installed on slopes up to 70 degrees if the slope is globally stable. So geocell slope protection is a complete system for ease of installation and peace of mind. So a little bit on walls. Geocell walls can be gravity or reinforced. Gravity walls have a limited wall height up to about 3.5 meters, but it depends really on the subgrade and the surcharges above the wall. A typical batter for a geo wall is 80 degrees, so basically near vertical. The wall panels come at different section lengths, so the design can vary to meet the site conditions. Reinforced walls have basically unlimited heights. Walls typically have geogrid reinforcement, which provides the stability. Panels are very flexible and be cut to accommodate various site conditions or pipe penetrations. And here you can see in this picture, this was actually 3 cells in depth. So 3 cells in depth, a little about 1.5 meters. So you can see how they just basically cut around the geocells. You can see the cut pieces right here to allow for these pipe penetrations for guardrail posts. You can see a reinforced wall adjacent to a rail bridge abutment. The walls are designed to include the surcharge loadings from the rail above the wall. And the wall in this application was basically used to limit the back slope from the rail above and for global stability. As a rule of thumb, we typically recommend keeping that back slope at about 2-to-1 angle. So keeping this about 2-to-1 for global stability. This wall was put into place because their right-of-way was very limited. So this is another project, reinforced geocell wall in a right-of-way. The wall was used to prevent the slope from global failure and to stabilize the area. So after constructing this wall in late fall, it was hydroseeded for vegetation the following year. And here you can see the same wall in the summer, the following year. It can be seen that the wall blends in very nicely with its surroundings. Majority of geocells are vegetated. The vegetated walls are advantage of geocell earth retention system. The walls can be vegetated for a variety of reasons, including aesthetics and actually for stormwater reduction. To design geocell walls, you can use any wall, pretty much any wall software. We offer a free software for designing retaining walls and slopes called GeoMSC. It's available on our website for free. You can design any geocell wall for any green slope very quickly. You enter the wall parameters and it provides a free design input. The software is written by Doug Lashinsky. It can be thought of as an extension of a software called RISA. It is highly versatile and can model a range of site conditions. It can be used with walls and slopes, can perform both internal and external stability calculations. So the software is very used, and there's training videos available online. Software also allows you to pick different cell sizes and depths. No matter how you design a geocell wall, please consult with the manufacturer to make sure you're using the correct design parameters for their specific material. So a quick summary, geocell earth retention. Geocells can be used for gravity and reinforced walls. The walls are very flexible. The front fascia can be filled with topsoil and vegetated, or aggregate or concrete for non-vegetated wall faces. So once again, make sure the wall design is accomplished using the proper computer software, and it is based on the design parameters of that material. So with that, kept it to the 45 minutes. So thank you so much for attending. Really appreciate taking time out of your busy schedule. If any questions come up after the presentation, my contact information is here. So I guess if there are any questions, we can take a look at them now.
Yes, thank you very much, Brian, for a very comprehensive and interesting presentation. So yes, you've got quite a few questions in the chat. So what I shall do, if I pick them out, and then if the person would like to unmute themselves and ask the question themselves. So first of all, we've got Rami Shaltut from Coventry University. Rami, would you like to ask your question?
I can actually read them too.
Okay.
Yeah, Rami, I'll just read it. I guess the first one is, to what extent the use of Geocell enhances the vertical or overall track vertical stiffness? What is the percentage of improvement? Typically from the research and testing that we've seen and other, there's hundreds of research papers on geocells out there in the industry, and typically it's at least 50%. And you can see that the testing we did with the with network rail on the northern hub, you can see those vertical sediments, decrease from 7 to 9 millimeters down to basically 1 millimeter. So it's a pretty significant improvement in stiffness. Question 2, do you consider applying geocell in sub-ballast layers and ballast layers? In case, what is the difference in terms of settlement track stability? So we typically always want to keep geocells, and actually any geosynthetic for that matter, whether it's a geogrid or a geotextile, outside of the ballast layer in case they have any tamping in the future. So depending on that real specific minimum ballast thickness, whether it's 200 or 300 millimeters, we want to keep the geocell, or like I said, any geosynthetic, out of that ballast layer. So typically for geocells, we want to keep it as high as possible in the sub-ballast layer. So they'll have the ballast layer, and then right below the ballast layer, we'll put the geocell, because the higher up in the cross section, the better the stress reduction.
Thank you. Thanks, Brian. I see the next question from Ismail is more about just looking for points of contact, which you've given in the presentation. And yes, Ismail, the presentation will be available on the PWI website, so you can get in contact there. You've got all the contact details. I'm sure that will be fine. And then our next question is from Rob Clark. Can you see that one, Brian, or Rob, are you there?
Yeah, renewals in the UK under increasing time constraints, possession time, etc. How would renewing removing the geocell impact the renewal process when it becomes life expired? So I mean,
and could I add something on there, Brian? I'm also interested to understand, have you actually come across a situation where you've seen any geocells installations that are now life expired?
No, not really. I mean, like I said, the geocell life is hundreds of years. It's made of 100% virgin HDP typically. It has a life of over 150 years when it's subjected to 100% 24-hour 365 UV exposure. That's even before the carbon black or the UV inhibitor starts to degrade. So once you bury it in the ground, the service life is pretty much going to be there forever. I guess that's the big reason why it's so important to work with the geocell manufacturer to get a design in a cross section that's correct. You're using the correct size of geocell, and you're also using the correct depth, and also the correct geotextile. A lot of times here in the States, we've seen issues, and I've actually seen it in Australia, and also in Europe, where the engineer has used, or the manufacturer has recommended, a slip tape woven geotextile, which is a high strength geotextile, but it doesn't allow drainage. And what happens is the pore pressure or water pressure buildups below the geocell, and over time it leads to global failure. So you got to make sure you use not only the right geocell, but also the right geotextile separation layer. Okay,
so I guess in answer to Rob's question then is you haven't come across this scenario yet about trying to take it back out?
No. I mean, we had areas where they had to remove geocell to replace, say maybe some site utilities or, pipes underneath the track. And that's very easy to do. They just, with a typical excavator, you just rip it out, and then you just, just like any type of geosynthetic, you just go in and put in new geocells and butt it up to against the existing.
And then the next question from Rob Mashford. If you're using geocells, does that mean you can't use a ballast cleaner in future years?
No, you can use the ballast cleaner. Like I said, we try to keep it out of the ballast layer, and it's always in the sub ballast. So yeah, not a problem.
Okay, good stuff. And then Gary, well, we've talked about this. What's the normal life expectancy of the geocell? So that seems like it's a very long time.
Yeah, and what cell heights are available? Have a different requirement for height, and those can be cut. Typical under a rail. Network rail has used a lot of 200 millimeter depth in the past, but typically we're seeing a lot of, with the advancements in the enhanced woven geotextiles, providing a lot of strength, we're going to a 150 millimeter geocell. Network rail actually did some testing at TU Klostall in Germany, based on, Presso's testing at University of Kansas. And they actually used to use a 300 millimeter Geocell, but it was shown through the testing that it's very hard to compact that 300 millimeter Geocell panel. And that's why Network Rail pretty much standardized with a 200 in a 150 millimeter deep Geocell.
Okay, thank you. Yes, the slides will be on the PWI website. So then Thomas Utley, can the grids be installed without full excavation of the ballast?
Well, like I said, if it's kept out of the ballast layer, you know, to keep the tamping issue, that's the next question too, is tamping the damaged Geocell. So we want to make sure we always keep it out of the ballast layer, or whatever the tamping depth is. I know we do a lot of work all over the world, and a lot of railroads use 200 millimeter ballast, some use 300 millimeter ballast, some use 250. So we always want to keep that Geocell out of that ballast layer.
Okay, and then can you see Matthias Stewart's question?
What is the difference in productivity of a Geocell formation compared to a traditional granular formation? The Geocells are installed very quickly. You know, typically you're pre-staging. Usually it's 2 panels in width across the track bed. So you're pre-connecting 2 Geocells at a time. And then you're basically hauling them over and connecting them to the panels that are already in. Typical, you know, rates are about 300 to 350 square meters an hour for 3 people. So it goes in, you know, very quickly.
Yeah, and then the rest of the questions, Brian, they're all similar around the topic, aren't they, about the depth and tamping machines and how long is it going to last for?
Yeah, there's one question. You say 150 years life. However, what guarantees come with the design? As many designs request many years life. You know, I guess we're not engineers, so we don't actually, you know, certify or stamp any designs, but we do actually certify our product is in conformance to the specification and does not degrade over the service life that you're looking for. So we have no problems. We've actually provided 50 to 100-year service lives on many projects that our material will hold up to spec and will not degrade.
Okay. Well, I think we'll come to the end of the questions that are in the chat. Just an observation, Brian, it's very interesting looking at your photographs and seeing, you know, different railway administrations around the world and the requirements for PPE. They're quite variable, aren't they? And great to see as well some, you know, projects that people here in the UK, if most people on this call are in the UK, will recognise on Network Rail.
Yeah, Network Rail's done a lot over the last probably 5-6 years with Geocells. You know, Mohammed and Levante at Network Rail were very interested in really pushing the technology to save, you know, time of construction and costs.
Yeah.
And they put a lot of time into developing that guide that can be used.
Yeah.
And you know, Geocells are not a save-all for every single project. You know, they have their place in the industry, just like geogrids and geotextiles. So, you know, it's good to reach out to the manufacturer to discuss the project. Show them your soil borings, show them your rail details, and let them provide a full design so you can, I guess, rest peacefully at night knowing that the railway is going to work just fine over the life of the project. Yeah.
Yes, I'm actually a bit surprised that Levente's not on the call today. We've just had another comment in there from Matthias, I think, who's in New Zealand.
So in New Zealand, we have subgrids less than 2%. It's been recommended to stack Geocell layers. Have you utilized this method? Yes. Actually, we've done quite a bit of work in New Zealand and in Australia. I would not recommend stacking Geocell layers, not because it doesn't work, but because it's not that cost effective. So what we typically do when you need more ballast or sub-ballast underneath the Geocell, what we'll do is we'll actually put down a high strength woven geotextile, and we'll build up a sub-ballast, say 150 to 200 millimeters. And what we do is we wrap that geotextile around, so almost like a burrito wrap. And then we put the Geocell layer on top of that, and then the ballast layer. So yes, you can, but if I was providing you a recommendation, even if it's less than a 1 CBR, we typically go geotextile, sub-ballast, wrap the geotextile around that sub-ballast, and then Geocell on top. That'll give you a lot more cost-effective installation than using 2 layers of Geocell.
Right. Maybe Matthias will be in contact with you directly then, Brian, for a bit more advice on that one. And it's
yeah, I know
we've got someone from New Zealand.
Yeah, I know I'm selling against myself, but like I said, the advantage of using two layers of Geocell is it's just not cost effective.
Right. Okay. So we haven't got any more questions or comments, and we're finished a little bit early. But on behalf of the PWI, Bryan and Laura, thank you very much for an excellent technical presentation. Going right through from the theory, research and development into practical applications and demonstrating the benefits. You've had a good audience today, I think. I saw nearly almost 80 people on their call. I think someone's actually got their hand up. So does someone want to ask a question? I can see if someone has their hand up. No, I can't see any hands up. So I think we'll call it a day there, Bryan. So Bryan and Laura, thank you very much once again. Really great presentation. Thank you.
Thanks.
Okay,
Thanks a lot.
I'll send over the PDF of the presentation.
Brilliant. Thanks a lot,
Right.
Bryan. Thanks ever
Yep.
so much.
Cheers.
Bye.
Everyone. Bye.